In this next module, I'm going to show you the distribution of some common statistics, a mean, an odds ratio, and a correlation coefficient. In order to illustrate all of these, I'm going to use some example data, some made-up hypothetical data. These are actually computer-generated data. I had the computer generate some data, and it's loosely based on a real example in the literature about that study was looking at middle-aged and older European men, and it was looking at vitamin D levels and cognitive function. So I loosely based my made-up data on that study, but it's just nice to have some toy data to play with this week. There's two statistics that we're going to look at from my hypothetical data. I chose a sample of 100, so my sample size here is 100 in my hypothetical data. We're going to look at the mean vitamin D levels in those 100 men, and we're going to look at the correlation between vitamin D and cognitive function in those 100 men, and cognitive function was measured by a particular test, the digital symbol substitution test. And for the purposes of generating this made-up data, I assumed that the true mean vitamin D in all middle-aged and older European men is somewhere around 62 nanomoles per liter, and the true correlation coefficient between vitamin D and IQ function, cognitive function, was 0.15, which is a very weak correlation. So let me just illustrate for you this hypothetical made-up data. So in the sample, I have a sample of 100 men, and I've got their vitamin D levels, and I've plotted those vitamin D levels here in a histogram. So notice that the vitamin D levels in the sample follow a right skewed distribution. That makes sense with something like vitamin D because you can't get lower than 0, but vitamin D can get quite high in a handful of people, so you get this tail out to the right. The mean vitamin D turned out to be 63 nanomoles per liter in my sample, and the standard deviation was 33 nanomoles per liter. Here's a graph showing the correlation between the vitamin D levels and this cognitive test, the DSST score. Higher values on that cognitive test mean better cognitive function. You can see that there's a small, very weak positive correlation between vitamin D levels and cognitive score, and I built this into my made-up data, very small, weak correlation here. You can actually calculate a statistic that quantifies that correlation. It's called the correlation coefficient, and it comes out here to be a value of 0.15. Some of you may have heard of correlation coefficients before. If you haven't, a correlation coefficient is this nice little measure because it's unitless. It's a value that ranges from -1 to +1. If you're at 0 or somewhere close to 0, that means that those two variables are uncorrelated. You're measuring the correlation between two variables. So 0 would mean uncorrelated. +1 would mean perfect positive correlation. -1 would mean perfect inverse correlation. That is, that if vitamin D levels went up and cognitive function went down. And anything in between +1 and 0 or -1 and 0 is some kind of in-between amount of correlation. So 0.15 is pretty close to 0, so it's a very weak correlation. But the correlation coefficient in the sample of 100 came out to be 0.15 here. So how would I figure out what's the distribution of the mean here? So we're going to use the mean vitamin D as my example. What's the distribution of the mean? How can I figure that out? Well, I'm first going to figure it out by running a computer simulation. So here's how the computer simulation works. I'm going to tell the computer that there's some large population of men, European men, and I'm going to tell the computer the distribution of vitamin D in this large population. And I'm going to tell the computer it's a right skewed distribution, so vitamin D follows a right skewed distribution. It has a standard deviation of 33, and let's say that the true mean value in the population is 62 nanomoles per liter. It doesn't matter too much what I pick there, but let's say I'm going to pick the value of 62. So I tell the computer this is the population you're sampling from, and then I have the computer sample a random sample of 100 virtual men from this underlying population. Each of those men is going to have a vitamin D level. I take those vitamin D levels and I average them to calculate the mean vitamin D level for that sample of 100. Then I'm going to repeat the experiment over and over and over again. Again, this is the thought experiment. I'm going to select a different random sample of 100 men, calculate their mean, and then I'm going to do that again and again and again to get a sense of the distribution of the means. I arbitrarily decided to do this 10,000 times. Again, 10,000 is a pretty large number, but not so large that it will hang my computer. And then we can explore the distribution of those 10,000 means. We can actually look at the distribution of the statistic here, and the statistic here is a sample mean. So here's the results of this computer simulation. What you're looking at is the histogram On the y-axis is the counts. Out of 10,000 times, how much did different outcomes, different means occur? On the x-axis is the mean vitamin D level. So this represents the mean out of 100 men in each sample of 100 men. So you can see that most often we got a mean of about 62, somewhere around 62, because remember the true mean in the population is 62, so that's not surprising. What else can we say about this distribution? Well, you might have noticed, and this might have surprised you, that it turns out to be a normal distribution. The means follow a normal distribution. This is a little surprising because remember, vitamin D, the trait, followed a right-skewed distribution. That distribution, that underlying distribution is right-skewed. But when we take the means follow a normal distribution. And we can prove this with a theorem called the central limit theorem. For those of you who are interested in that, there's an optional module on the central limit theorem. But it turns out that when you take averages, averages follow a normal distribution. Conceptually, what's going on here is you can imagine you're on this right-skewed distribution. There's going to be a very few number of people who have very high values. So you might get a man in a particular sample who has a value of 200, for example. Well, if you average that 200 in with 99 other men, that has the effect of bringing everything towards the center. So that 200 really gets diluted because you average it with 99 other men. So it ends up, when you take averages, it ends up bringing everything towards the middle, and it ends up forming a normal curve. The mean of the means, I'm going to say that again, the mean of the means, this is the mean of the means that we're talking about here. The mean of the means turned out to be 62 nanomoles per liter. Well, that's just the true value, the true mean. So that's not surprising. The mean of the means is the true mean in the population. Well, that makes sense because if that's the true mean, then most of our samples should hover around 62, the true mean. The standard deviation of the means turns out to be 3.3 nanomoles per liter. Now that's interesting. Remember that the standard deviation of the trait was 33 nanomoles per liter, but the standard deviation of the means, which we also call the standard error of the mean, turns out to be 3.3. It's exactly 33 divided by 10. Well, the sample size here was 100, so what we're actually doing is we're dividing the standard deviation by the square root of n, and that's what gives us the 3.3. This 3.3 I didn't get by a mathematical theory, though. I just had the computer calculate the standard deviation from these 10,000 observations, and it turns out to be 3.3. So the distribution of mean vitamin D that I got from this computer simulation, I see that it's normally distributed. The mean is equal to the true mean, and the standard deviation, or what we also call the standard error, is 3.3 nanomoles per liter. I got this all out of the computer simulation, but the distribution of a sample mean in general, people have long ago worked out with mathematical theory. And it turns out that if you're talking about sample means that you calculate from data, they follow, actually they don't exactly follow a normal distribution. If you want to know more about why that is, watch the optional module on the central limit theorem. It turns out that they follow a t distribution, but remember that a t distribution is essentially the same as a normal distribution as long as you're talking about n's sample sizes at least of 100. So since we have a sample size of here of 100, essentially it's on a normal distribution. This means that if you're talking about sample means and you're talking about small samples, actually small samples, you have to worry about it being on a t distribution. It will have slightly fatter tails than a normal. So it's not exactly, means don't exactly follow a normal distributions for real data. They usually follow a t, but by the time you're talking about a sample size of greater than 100, where it's interchangeable with a normal, so I'm just going to call it a normal distribution. In general, sample means, the mean of the means is the true mean in the population. Well, that makes sense. The standard error, somebody's worked out the formula for standard error. The standard error of a mean is the standard deviation of the trait, the variability of the trait like vitamin D, divided by the square root of n, the number of people you're averaging over. And that's, remember, we saw that in fact works out with exactly what we saw in the simulation, because the standard deviation here was 33. If I divide by the square root of 100, I get exactly 3.3, exactly what came out in the simulation as well. So both the simulation and mathematical theory are matching up. So the standard error of a mean, again, is the standard deviation of the trait divided by the square root of n. So you can see some things about how standard error works just by looking at the formula. The formula gives us some insight here. I'm not worried about you memorizing the formula, but look at the formula in terms of what is it telling us. So standard error decreases as sample size goes up because sample size is in the denominator. So bigger sample size means less standard error. Well, that makes sense. As you sample more people, you would expect the uncertainty to go down, the imprecision to go down. The variability of the statistic from sample to sample will go down if you're sampling more people. You're going to get closer to the true mean. The standard error increases with greater trait variability. That S, that standard deviation of the sample, is in the numerator. So if vitamin D were more variable, that's going to cause more variation in the statistic, right? That's going to cause more uncertainty. So those are the two elements of standard error. And just to illustrate those, I did another simulation where I increased the sample sizes to 400. So I did many, many, many samples of 400. Notice what happened to my normal curve. It shrunk. The standard deviation went down. The standard deviation in this simulation came out to be 1.7. My mathematical theory would predict that it would be 1.7. If vitamin D was more variable, let's say the standard deviation of vitamin D in the population was 40 rather than 33, you can see that that causes this curve to widen. The standard error goes up here, it goes up to 4, because if vitamin D is more variable, we get more variation in the means from sample to sample. So standard error, again, depends on the variability of the trait as well as the sample size.